Good evening. This is a course on geospatial analysis for both the Environmental Studies program and the Data Analytics program. There are different requirements for the two programs, and check your syllabus on Sakai for those requirements. This series of video lectures is an alternative to in-class lectures on campus. The logistics of the online program was sent in an email to the Data Analytics students. So we will proceed to the introduction of GIS in this video. And here we see the course topics that we'll be covering. A large part of it is going to be spatial analysis, and then we'll also have an introduction into the geospatial systems, geographic information systems with data collection and transformation, coordinate systems and projections, and we'll finish up with extending GIS with Python. A GIS helps us gather and use spatial data. We'll use the abbreviation GIS to refer to both singular system and plural systems. A key to all definitions of a GIS are where and what. GIS and spatial analyses are conducted and concerned with the absolute and relative location of features, the where, as well as the properties and attributes of those features, the what. A GIS aids in the analysis and display of these spatial relationships. A GIS is a tool for making and using spatial information. And here's the book's definition. A GIS is a computer system to aid in the collection, maintenance, storage, analysis, output, and distribution of data and information that has a location component. GIS help us identify and address environmental problems by providing crucial information on where problems occur and who are affected by them. They help us identify the source, location, and extent of adverse environmental impacts, and may help us devise practical plans for monitoring, managing, and mitigating environmental damage. Public organizations have adopted GIS because of legislative mandates and because GIS aid in governmental functions. For example, emergency service vehicles are regularly dispatched and routed using a GIS. Many businesses have adopted GIS because they provide increased efficiency in the delivery of goods and services. Retail businesses locate stores based on the number of spatially related factors. Where are the potential customers? What is the spatial distribution of competing businesses? Where are potential new store locations? What is the traffic flow near current stores? And how easy is it to park and access these stores? The societal push to adopt GIS has complemented and has been complemented by a technological pull in the development and application of GIS systems. In the past, thousands of lives and untold wealth have been lost because ship captains could not answer the simple question, where am I? Portable computing is one example of the technological pull driving GIS adoption. Each GIS user may decide what features are important and what attributes are worth recording. For example, forests are important to us. They protect our water supplies, yield wood, harbor wildlife, and provide space for recreation. A GIS is also particularly useful at displaying spatial data and reporting the results of spatial analysis. In many instances, GIS is the only way to solve spatially related problems. GIS are widely used to improve public health. Air pollution is a major cause of sickness and death, primarily from nitrogen and sulfur dioxides, carbon monoxide, ozone, and small particles from oil, gas, charcoal, and wood combustion. Many businesses adopt a GIS for increased efficiency in the delivery of goods and services. Retail businesses locate stores based on a number of spatially related factors. Where are the potential customers? What is, again, the spatial distribution of competing businesses, traffic flows, and parking? GIS are used in hundreds of other business applications to route delivery vehicles, guide advertising, design buildings, plan construction, and sell real estate. GIS regularly help in the day-to-day management of many natural and man-made resources, including sewer, water, power, and transportation networks, as well as mandated reshaping of U.S. congressional districts, and hence the distribution of tax dollars and other government resources. Emergency service vehicles are regularly dispatched and routed using a GIS. 911 callers and addresses are automatically identified by the telephone number. The GIS matches the address to the nearest emergency service station. A route is then immediately generated based on street network and traffic, and emergency crews are dispatched from the nearest station. The societal push to adopt GIS has been complemented by a technological pull in the development and application of GIS. The technological pull has developed on several fronts. Spatial analysis in particular has been helped by faster computers with more storage and by the increased interconnectedness via Wi-Fi and mobile networks. Most real-world problems, spatial problems, were beyond the scope of all but the largest government and business organizations until the 1990s. GIS computing expenses have become an afterthought today, as computing resources often cost less than a few weeks' salary for a qualified GIS professional. Costs decrease and performance increases have been occurring at a dizzying rate. Remarkable positioning technology, known as the Global Navigation Satellite Systems, GNSS, is now incorporated into cars, planes, boats, and trucks. GNSS are indispensable tools in commerce, planning, and safety. In addition to the computing improvements and the development of GNSS, cameras of today deliver amazingly detailed aerial and satellite images. GIS are needed in part because human populations and consumption have reached levels such that many resources, including air and land, are placing substantial limits on human action. Human populations have doubled in the last 50 years, surpassing 6 billion, and we will likely add another 4 billion humans in the next 50 years. Human impacts on the environment have spurred a strong societal push for the adoption of GIS. Conflicts in resource use, concerns about pollution, and precautions to protect public health have led to legislative mandates that explicitly or implicitly require the consideration of geography. In terms of economic activity, we need innovative analysis and visualization technologies like GIS, and these GIS systems are powerful tools. We have two basic strategy choices in economic competition: improve our operational efficiency or differentiate ourselves from current competition by adding new features and attributes. The purpose of either choice is to become more competitive in our environment. This is critical in the modern global economy because technology, especially improvements in microcomputing and telecommunications, have been applied to both administrative and manufacturing processes to raise productivity. Furthermore, emerging countries have become industrialized and now provide an overabundance of product and service offerings. It's estimated that China alone could meet the entire world's demand for goods and services. To survive, an organization must use innovative analysis to distinguish its products or service from others, or to improve its processes to become more competitive. Project complexity began to increase in the late 1970s and skyrocketed in the 1980s. Average project value remained relatively flat, around $17 million, from 1960 through 1976. In 1978, average project value started a parabolic rise to reach $80 million by 1984. This is an indicator of the increased complexity of the systems we're developing. Another factor increasing complexity is that product life cycles have begun to shorten. In the 1990s, the time to market pressure and shortened life cycles had a profound effect on organizations and their need for innovative analysis. Our world is changing from a labor-based economy to a knowledge-based economy. We know more than we can tell or write. This is tacit knowledge. In contrast, our explicit knowledge, our speech and writing, is only what we think is relevant, and it may not be entirely informative to every pursuit. The business world is undergoing a fundamental transformation from mass production, where human labor was the principal source of value, to a new era where the principal component of value creation, productivity, and economic growth is knowledge. The intangible assets, and this includes patents, know-how, and a skilled workforce, now account for over half the total market capitalization of U.S. public companies. McKinsey has divided the work in organizations into three categories: transformational, and that's the extraction of raw materials and its conversion to output; transactional, and these are interactions that can be easily scripted or automated; and tacit. These are complex interactions requiring a high level of judgment. Currently, tacit jobs are growing 2.5 times the rate of transactional jobs. There are two implications in these trends. The first is intellectual capital has become a key source of value, and two, knowledge workers, those who generate intellectual capital, are critical to the organization. So in summary, firms cannot survive in a low-cost world of overcapacity without strategies based on innovative analysis, because existing markets are saturated with supply. As a consequence, companies must differentiate their product through tools that help leverage their analysis, and data visualization techniques are tools that excel at this. And we'll see that in Lecture 2. We'll go into more on data visualization. The art of cartography has evolved over millennia, from cave walls as mediums to clay tablets, parchment, paper, and now digital formats. Maps have also gotten more detailed, as well as more accurate, as technology has been developed and improved. In fact, most of the world would probably have a hard time recognizing the most primitive maps as maps at all. It took mankind a long time to go from cave walls to mass-produced road maps. But the degree of change in the last few decades has been staggering. Geographic information systems, these are the GIS systems, have become more common and easier to use, giving more people the ability to analyze spatial data and produce their own high-quality maps. Next came web mapping and services that allow users to make custom maps online and then share them with concerned parties. Most of us even carry devices in our pockets that can display a map showing our current location and tell us how to get to a new restaurant that we want to try. Not only that, but the available data has also changed dramatically. Makers of those early maps would be blown away by our road maps overlaid on top of aerial photography and our talking GPS units, such as smartphones and Garmin navigators. Thanks to these recent advances in technology, along with free and open source tools, you have access to powerful software that you work with Improved data management is another reason we would want to use a GIS. We have big data capabilities with a GIS. We have data integration and transformation, where we can get data from many different sources and integrate them together. And spatial analysis in particular has been helped by faster computers with more storage. They have advanced spatial analysis capabilities. We can now resolve spatial problems that were beyond the scope of all but the largest government and business organizations up until the 1990s. The cost decrease and performance increases, as mentioned, are steadily increasing. In addition, we have GIS on rugged, field-portable computers, and that's been especially useful in field data entry and editing. A GIS will automate repetitive tasks. Modeling and visualization are used by data analysts in their work for both communications to other people and for analysis in their own study. So a GIS is something that helps in both regards. Visualization leverages our perceptual thinking as well as our analytic, and a GIS is a very powerful visualization tool. Advanced satellite imaging allows us to track the eruptions and plumes of volcanoes, and new space-based surveying aids in the planning, evacuation, and mapping of the damage that results from natural events. GIS spatial analyses help ensure sustainable recreation, timber harvest, environmental protection, and other benefits. Spatial data, such as the boundaries of prairie dog colonies and of individual black-footed ferret positions, may be combined to help us understand how to best save and preserve black-footed ferrets and their inclination to be close to prairie dog colonies. So, a GIS is composed of both hardware and software components. Because of the large volumes of spatial data and the need to input coordinate values, GIS hardware often have large storage capacities, fast computing speed, and the ability to capture coordinates. Software for GIS are unique in their ability to manipulate coordinates and manipulate associated attribute data for those coordinates. A number of software tools and packages are available to help us develop a GIS. While GIS are defined as tools for use with spatial data, we must stress the importance of an institutional context into which the GIS fits. Because GIS are most often used as decision support tools, the effective use of a GIS requires more than the purchase of hardware and software. Trained personnel and protocols are required if the GIS is to be properly applied. A GIS may then be incorporated in the question, collect data, and analyze data, make a decision loop when solving problems. The GIS system we'll be using this semester is QGIS. QGIS is an open source software project that's an initiative under the Open Source Geospatial Foundation. The software is a collaborative effort of a community of developers and users. QGIS has an interface into GRASS. GRASS was a comprehensive GIS system developed by the Department of Army, and it was released to open source because it was funded by taxpayer dollars. QGIS, as mentioned, is an open source, and why would we use an open source package? Well, there's several different types of open source license exist, and some of these not only allow you to modify the code as needed, but even allow you to turn around and sell your derived work without providing the source code for your modifications. Other licenses require that if you use the software, then your software must also be open source. The leading package on the market is a commercial package known as ArcGIS. The full license for ArcGIS can cost $7,000. Less expensive licenses provide correspondingly less functionality. With QGIS, you get all functionality for free. QGIS is free, stable, and it changes smoothly through time. The source code is available so that it can be extended as needed for specific tasks. It also provides a graphic user interface, supports a wide variety of data types and formats, and runs on Unix, Mac OS, and Microsoft Windows operating systems. GIS software provides the tools to manage, analyze, and effectively display and disseminate spatial information. A GIS by necessity involves the collection and manipulation of coordinates. We must also collect qualitative or quantitative information on the non-spatial attributes of geographic features. We need tools to view and edit these data. We need tools to manipulate them, to generate and extract the information we require, and produce the materials to communicate the information that we have developed. GIS provides the specific set of tools for all of these tasks. Most conceptualizations view the world as a set of layers, as we see here in this slide. Each layer organizes the spatial and attribute data for a given set of cartographic objects in the region of interest. These are often referred to as thematic layers. As an example, consider a GIS database that includes a soils data layer, a population data layer, an elevation data layer, and a roads data layer. The roads layer contains only roads data, including the location and properties of roads in the analysis area. A GIS is a type of database, and in generalized database design, it's important to organize data into themes to prevent redundancies and update anomalies. I'll go more into detail on this in our lecture on tables, lecture 4, but also I spend a great deal of time on it in my Systems Analysis and Design course, CIS 287. But mention it here to reinforce the idea that themes, in other words these layers, are a standard way of organizing data. Here we see an overlay of several different themes. It shows rivers in dark blue, roads in light blue, various facilities like hospitals and county offices and military facilities in yellow, green, and red. Each of them are a separate layer that are combined together to produce a map that is specific to our particular interests. Spatial data is often stored separately from attribute data, and this is the case in QGIS. And here we see a map of the United States and certain cities highlighted, and each city has one attribute record that has several characteristics of the particular city that we're interested in. Since we're interested in banks in this particular one, it gives us the name of the bank and other information about the bank in that particular city. And here we see a look at an attribute table. So in addition to the geographic data, we have non-spatial attributes that we associate with geographic features on our map. And those attributes or characteristics are stored in tables like relational databases. And here we see an example of one of the tables, in this case information about banks. And here's the process we go through in geospatial analysis. We have a question or purpose for our study. We then collect source data, and these are going to be features that have a geographic component, and there are going to be characteristics about that particular feature that we're also interested in tracking. So it might be a distribution of failed banks in the United States, and then we'd have a location for each failed bank, each city they were located in, and then we'd also have attributes of a failed bank. So on the left-hand fork, we go into geocoding with the location information. So we'll collect the location feature of features and the attributes related to a feature. Once we have the features that we're interested in geocoding, we'll do data input, And that can include, depending on the feature we're looking at, we might have to digitize it by using a surveying technique or some other technique. Or if it's a bank that has an address, we can use a geocoding program to change that into longitude and latitude. Then once we have that, then we'll look at coordinate transformations, making sure that our coordinates are the same in all the layers we want to use in our analysis. And then we'll project the coordinate system we have onto a map. That'll be combined with our spatial data, our non-spatial attributes that we likewise store in our spatial data store. And then we are then able to do queries and create models and other representations of the particular problem that we're studying that has a geographic component as well as non-spatial attributes that are associated with the geographic component. Both the non-spatial attributes and the geographic features are combined so that they can be accessed together. So that concludes our brief introduction to Geographic Information Systems, GIS. We'll go into much more detail in the next several lectures on coordinates and transformations and data models, and also the data stores that we use to store all of this information, both spatial and non-spatial attributes. And then we'll get into more hardcore geospatial analysis after that. Thank you, and I'll see you in lab. And also we'll be working on forum questions online and in-class questions at the campus at Shepherd University.